Okay, just say okay. Well, now you are in session, I think. Let me check. We are in session. See, 8, 9. But I think we have to put it back to this one.
Presentation, yes.
I think you're already in presentation. You see, and then we put here display, and that will be duplicate. See? Okay, go ahead.
Yes, thank you very much. So, welcome back, guys. This is the second part of the presentation, which actually the concept selection process will start. So the concept selection is mainly one of the major tasks for surface facility team. So to just get aligned with the previous part of the lecture, as we mentioned, a concept selection is a subset of field development planning. And exploration and appraisal phase provide required information for concept selection. And success of concept selection phase highly depends on the quality of the data provided in the previous phase. So actually, as we explained before, subsurface drilling and completion teams make multiple depletion scenarios, including well count, location and type, drilling and workover and well intervention requirements, production profiles, fluid composition, recovery methods, and blah, blah, blah. And then surface facility team makes corresponding development scenarios, including field subsea architectures, host unit, including hull type, mooring and riser system, workover and well intervention package, and exporting methods for each depletion scenarios. And beside them, commercial and management team will calculate net present value, net present investment, and risk assessment for each of the concepts to make a final decision. Concept selection processes actually can be divided into two phases. Concept screening, which are called concept screening, and concept selection process. Actually, they are quite similar to each other, but there are the main differences in the accuracy of the data. So here, in the first step, you have to define your concept or selected concept. But for concept screening phase, you only define primary systems. For example, based on your well stream, you only know that you need 2 separations with this capacity. But you don't design all the piping system and everything there. But for concept selection phase, you need basic design of the unit. You need more accurate data. So you need some design documents as well.
What is feed?
Feed is front-end engineering and design. And for even some companies, especially major oil companies like Shell, BP, when they are in the concept selection phase, they even hire some contractor to make a pre-feed them for them. And then in order to have a more accurate estimation of the price and schedule for that concept. So the major differences is on the accuracy of the information we have. Because for both we have a cost estimation, we have a risk assessment, we have qualitative and quantitative ranking. So for concept screening, cost estimation is cost class 5, which we'll explain later. And for concept selection is cost class 4. Risk assessment for concept screening is optional. Maybe operator decide to make a risk assessment in this stage or not. But for concept selection is mandatory. You have to do risk assessment for final decision. We have also 2 types of general ranking systems, quantitative or qualitative ranking. So qualitative ranking, when you are doing qualitative ranking for concept screening, you just define the functions or properties into attribute levels. But when you are doing concept selection, you have to define functionalities or properties more accurately, which is called sub-attribute level, which we'll explain later. And also a stochastic analysis, because you are just planning based on some uncertainties, it is quite common to make some stochastic analysis to relatively consider the effect of different parameters. But a stochastic analysis for concept screening is mandatory. Why? Because here your parameters are much more uncertain than concept selection phase. But for concept selection phase, a stochastic analysis is usually optional. But they both together, they use similar process, but different, as we mentioned, in accuracy and level of implementation.
Can I say something? When you say mandatory, I mean you have to. Who decided you have to? Well, you have to realize the biggest partner in Norway, or in any other place in the world, is the mineral owner. Here in Norway, the government, they have a share of 80% of all that you have. And they want to make sure that you do your homework, and they want to be able to audit you. Then you have partners. It's a joint venture. You have to make sure that the operator doesn't cheat the other partners. Then the operator is in the stock exchange, in New York Stock Exchange, in Oslo. So they want to make sure that they don't cheat the public. They tell you, oh, we have such a big, huge reservoir. And then everyone run to the stock exchange and buy stock of BP, and buy stock of Statoil, buy stock of Shell. So there is regulation here. What is mandatory? You cannot say we have big, you know, like they say in South America. You do a lot with the hand, big reservoir. Listen, I want to see this expectation here. 100%, because some company cheating, they report the 10% probability, and they say this is the reservoir. But it's only 10% that you get that reservoir. But meantime, people run to the stock exchange. So there is a lot of regulation. What is mandatory by the stock exchange, by the government, by the partners, and by the banks that give you the money. So this is why it's mandatory, it says here. It's not that you think it, that your boss thinks it's mandatory. Someone tell him it's mandatory. Okay? It becomes public, or it becomes maybe confidential, but it goes to the government, goes to the student. It's not right?
Yes. So in the beginning of concept selection and concept screening phase, a facility framing workshop is made with representative from all stakeholders present early in the selection phase. So everybody sit together in the same room, and the purpose of this workshop is to establish the objective of the project, strategies to reach this objective, establish design basis and fundamental requirements, generate concept development matrix, generate initial development scenarios, and develop decision drivers and ranking methodologies, which we'll explain one by one in the following slides. So in the concept screening, the main input is field depletion scenarios made by the subsurface and drilling and completion team. And then we should make or establish basis of design and functional requirements based on these depletion scenarios, and as well as ranking criteria and methodology in order to compare different concepts with each other. After that, this team or workshop will identify basic building blocks from proven technology. For example, for host unit, you know that for this water depth, you can have 3 different floating production units. And we start the first stage, which is concept screening. And for this stage, you need to define your concept up to some level sufficient for this stage. So first stage definition is performed, and then we combine different building blocks with each other to generate different development scenarios, which can be up to 10 to 18 scenarios, for example. This is just some relative numbers that you know that in concept screening you have much more number of concepts than concept selection phase. And also you make a ranking and comparing different scenarios qualitatively and quantitatively in order to reduce the scenarios to sufficient number of scenarios for concept selection, which let's say it will be 5 to 10 scenario at the end. And then you go to concept selection phase, which you need to define your concept more accurately. So in the concept selection phase, you have a second stage definition. You may need to do some analysis. For example, usually in the concept selection phase, we will make some process or topside simulation and analysis by HISIS to accurately specify the size and dimension of the equipment for topside, which can be later used for weight estimation. But in concept screening, you just you know that okay, I have this 40,000 barrel per day production, and for this you from some basic tables you know that the size of the separators, the size of the heat exchanger will be this amount, which is some one-to-one relation between the capacity and flow rate. So, and in second stage in the concept selection, you make again ranking and comparison, but with much more information and more accurately, until you end up with one solution. But many times you don't. It's not a straightforward decision. After you compare the result with each other, you cannot say, okay, this is the final solution. Usually you end up with 2-3 solutions that we'll show in the example later. And here that operators usually use their tiebreakers, or in the other way we can say they can use their main strategies to make a decision. And finally one solution came out, and also you have to make international benchmarking for final solution, or compare your final solution with available solutions in the world, in different parts of the world. For example, if you are planning a concept for 800 meters water depth, then you take a look at the other solutions in the world with the same water depth to see if they have used similar concepts or what have been their experience.
When we do the qualitative analysis, what things we see in the different scenarios?
This is, I will explain later exactly which quantities or which parameters we are comparing.
In qualitative analysis, we also compare the different quantities.
Yes, but the quantities which actually qualitative parameters are parameters which cannot be directly related to cost, because there are in general two major quantities which make a decision: cost and time. But if you can directly relate the characteristic of parameter to cost and time, we consider it as quantitative. But if you cannot, then we consider it as qualitative parameter. And there is two different systems for ranking with this quantitative and qualitative, or even qualitative parameters. At the end, you should establish some system to characterize qualitative parameter, which we will show later. I mean, you have to end up with some numbers, otherwise you cannot make any decision. So as we mentioned earlier, it is a two-step process: concept screening and concept selection. In concept screening, the main goal is to identify all the possible solutions, because without comparing accurately, you cannot say which one is better. But there are always some brave people in the company. In the beginning of the exploration, he said, okay, I'm sure this is the best solution for this field, but nobody believed that. And then in this step, we make some technical feasibility to just identify the technical feasibles or technically feasible solutions from all the available solutions. And we make some economical viability. We make some rough cost estimation, which is known as cost class 5, to reduce the number of scenarios to, let's say, 5 to 10 scenario sent for concept selection phase. Sometimes for marginal fields and in deep water, even the number of wells can be one of the main parameters during concept selection, because you have to evaluate the effect of number of wells on the net present value and net present investment. And in concept selection phase, main objective is maximizing the profit. And also you have to select best concept. Therefore, you need more accurate cost estimation and assessment. So, one of the documents we mentioned we have to make in the beginning of the concept screening and concept selection is design basis document. In fact, this document provides the framework and the constraint within which the development team must operate. For example, for our company as a contractor, the first document we receive from any operator is basis of design, that everything is clear there enough, and then we review this document and we ask the operator whether we need more extra data or not. So this document usually as a minimum should include this information: reservoir characteristics and depletion plan, which you know, drilling and completion, and site and regional considerations.
Are you a company doing just design on contract, or you provide equipment? What actually is
It depends on the requirement from operator. If operator requires, we can just get the basis of design from operator and give them the floating platform unit at the end. But it depends on from operator. For example, Shell is usually take care of all the procurements and everything. We're just only doing the design for them. But for example, for Goliath field, for any was more open to us. For example, they ask us to give supervision during construction, or almost all the procurement for the top site has done by one of our.
But who selected this type of round shape?
This is the decision of the operator.
Operator decided
Yes,
that.
decided that.
And they regret it now or not?
No, they accepted it because it's now on.
I know, but they regret it now or not? I think they maybe could have tied back straight to shore without floating vessel there, or
No, I think they are quite satisfied with that.
oh, they have to.
Yeah, they have spent a lot of money.
But you know, I think they go around and say, oh, if we knew what all we know now, we'd probably take much simpler solution. But never mind, go ahead.
Yeah, because just the motion, one of the benefits of the 7 is that we have less motion, as you mentioned, than ship shape unit, but motion is not the only decision parameter. There are several other parameters, and even it can, as you know, it can even change from time to time, because there are a lot of personal decisions involved in the concept selection phase, and this is why we need a stochastic analysis.
Okay, go ahead.
Yes, and also this team has to specify functional requirements, which is usually the responsibility of the contractor, like our company, to specify some basic functional requirements have been defined based on basis of design, but then contractor will also extend these functional requirements, like processing requirements can specify deck space and required payload, storage and export, which can directly specify the hull dimension and geometry, well access requirement, which can make some constraint for motion of the floating platform, drilling and workover requirement can again make some constraint for motion and deck space, and required enhanced recovery. But what is ranking methodology and strategy? In general, ranking methodology and strategy in any field can be divided or categorized in these 3 groups. It can be qualitative ranking or quantitative ranking. It can be deterministic or stochastic, and also based on the cost estimation accuracy, we can divide it into several levels. For example, qualitative ranking is usually used for uncountable parameters like operability, constructability, installation ease. And also when less accuracy is required, like during concept screening. And also mainly for technical issues. And quantitative ranking is usually used for countable parameters like cost, time and schedule, and it is required when more accuracy is required, like concept selection phase. There are several number of economic factors which you need to consider during concept screening and concept selection, like the price of all the equipments, the price of oil, the price of installation. But it's difficult to just compare all these parameters one by one for both concepts. Therefore, this significant number of parameters have been summarized into three main parameters: net present value, net present investment, and utility index. And also based on the stage of the project, for example, if you are in the concept screening, because your estimation is quite uncertain, therefore you need to do a stochastic analysis and Monte Carlo simulation to identify the contribution of each parameter in the final decision. But to make some guideline, American Association of Cost Engineering has issued international recommendation practice on estimation classification, which have been used in all industries. They have different cost classes based on the cost dispersion. And based on that, for our purpose, cost class 5 is usually used for concept screening and study, which you have a cost dispersion between plus 100 to minus 50. That means when you estimate the cost of one module, you know that your cost can be vary between, for example, you say, okay, the mean cost is $1 million, but it can be $2 million or it can be $500,000. And cost class 4, concept selection, when concept dispersion is between 50% to minus 25%, or in other way, your cost accuracy should be in this range, between 50% to minus 25%.
Are you using the weight of machine equipment and weight of structural material? Roughly, weight is 500 tons. It's going to cost you, half of it will be machine and half of it will be structural, and that roughly was going to cost.
For hull, the weight is important
but
parameter.
also for process, for example.
But for process, mainly the capacity of the, for example, capacity of the separator, the price is estimated based on the capacity, as a function of capacity. Because now, for example, there is a software called Oil and Gas Manager, which is developing by Siemens. Maybe if we have a time later, I can show this software to the class, which we have some cost table there, and these costs have some units. For example, it's $1 per barrel of oil, mainly for process units. Or it's, for example, for generator is as a function of power of the generator. For example, how many watt is that? Just rough estimation based on the capacity for topside. So also you have several non-economic factors, or better to say maybe qualitative parameters, which cannot be directly related to cost and time. And also they are main driver or decision drivers for operators, like construction period, operability, fabrication, reliability, and risk assessment. So these are mainly known as qualitative or semi-quantitative parameters. But these parameters can be usually divided into or defined into two main levels, into attribute, which is used for concept screening, and sub-attribute levels. Next example, which exactly show what does it mean. General decision drivers for non-economic factors are mainly minimizing technical risk, maximizing hydrocarbon recovery. I mean, concepts that give you less risk would be better concept. And constructability, concept which has easier construction. For example, one of the benefits of 7 unit is just composed of flat plate and circular plates, which is quite easy for construction. But when you go to the shipyard, you have very big challenge for making the bow and stern, which is the two end part of the ship. And then general decision, schedule to first oil, for example, concept which needs less construction period can give you shorter schedule to first oil. which is one of the main parameters for authority to approve your field development plan. And expandability, which is very important for future expansion, and the flexibility to adapt to reserve or uncertainty. As we made a previous example, for example, you don't know exactly how many risers do you need. And if you want to increase the riser, for example, when you select FPSO with disconnectable turret, which is very safe solution, and which is one of the major requirements for Gulf of Mexico. All the FPSOs should have a disconnectable turret. But in North Sea, you don't. This is not mandatory. This is optional. But when you have a disconnectable turret, then you have a limited size for number of risers. So then if you want to use this concept, FPSO with disconnectable turret with very uncertain field, then you may have a big risk here. So then also one of the main tasks during concept screening and concept selection is concept definition. Concept definition for concept screening phase should be up to level sufficient for cost class 5, capex, opex, and schedule estimation. For this kind of estimation, you can use like major oil operators. They have, because they have a long experience and they have a lot of databases, they usually use their available databases or in-house databases. But for a small oil operators that they don't have available databases, they usually use commercial databases like oil and gas managers, which have been developed recently. There are not so much commercial tools like oil and gas manager available in the market. And typical required input for concept selection is basic subsea equipments, like flue lines and length of flue lines, number of manifolds, Christmas tree and size, and number of risers, number of wells, production profile, hydrocarbon sale price, basic topside components and capacities, and type of host unit and required displacement. For example, the cost of host platform is usually estimated in this phase by displacement. It's very rough estimation. And then you calculate net present value, net present investment for this concept, and you compare different concepts based on the utility index, which is net present value over net present investment, as a function of net present value. And then you get some graph that you can easily find which concept is the best one. And maybe number of well can be also one of the decision parameters here. And finally, you choose the concept. The decision criteria is to choose the concept which has net present value or utility index threshold which you have defined, or if you don't have, you just select the concept that maximize net present value and utility index simultaneously. But when you are in concept selection, the objective in this phase is to define all the surface facility component to the level sufficient for cost class 4, capex, opex, and schedule estimation. For this,
these classifications, well, what kind of classification?
So this is the classification defined by this American Association of Cost Engineering.
Cost engineers, okay.
And then they have defined, for example, for offshore oil industry, to get cost class 4, you have to define your, for example, topside up to this level.
Do they have manuals or specification or something? In which document they have it?
I think yes, there is a recommendation practice for that. Yes, there is a recommendation practice available for it, but it's quite general for all industries, not as far as I know. Maybe they have some separated issues or appendices for oil and gas industry.
Because for refineries, it's simple, because each refinery is like cloning the other. Same elements, same pipe, so they have costs, but you come to subsea, you don't know what a piece of pipe costs. Who knows that?
Yes, it's very rough estimation, yeah.
Okay.
But in concept selection phase, usually you define your concept up to this level. I mean, you have to make size the flue lines, riser and pipeline. For example, in concept screening phase, you don't need to specify the size of flue lines. You just specify the dB and number of pipelines. And you just make a rough cost estimation. But in this step, you have to do flow assurance analysis to size your flow lines exactly, and usually they contact vendors to get a more accurate price. You don't just make a rough estimation. You contact the vendors and ask them to give you a price for that. Then you have a more accurate price. But even when you contact vendors, two vendors can give you different price, 10 to 15% different. And so you have to size the flow line, specify the risers and pipeline dimensions. With flow assurance simulations, you should specify the topside drilling and workover equipments and make an initial layout by process simulations. I mean, you have to even make a flow process flow diagram. Don't mix up this with probability density function. It's process flow diagram. And make a PNID for topside. I mean, the concept have to be defined up to this level. Then you can make a cost estimation for this class. And make an initial sizing of the hull to support topside riser mooring weight. For example, 3 years ago, Shell has contacted us for this Penguins field for concept selection phase. At that time, they just give us some information sufficient for this level. But after the concept was finalized, now we get into the concept definition phase. We just make more accurate design and make much more accurate cost estimation.
How many people typically on one concept do all these things? How long it take?
I think for topside, for hydrodynamic part and marine analysis part, I think 3 person. For machinery, 2 person. Topside, roughly 5-6 person. I think altogether we are a team of 15 to 20 people.
And 6 months, 3 months
For
that phase.
Around 3 to, depends on how. But for example, just make an example, which for Shell it was a 9-month project, but for Bream it was just 4-month project. Because we as a contractor, we always try to define some more hours and make more accurate estimation, but operators usually would like to have yes, quick estimation. But
So
I think
that's you know, in the past there've been let's say we've been 3 companies in Norway, Norwegian, Saga, Hydro, and Statoil, and they were in a joint venture, and each one operator and 2 just joint venture partner. Each one did all these studies. So been 3 companies and 5 concepts. So been 15, and it was a lot of work for the consultants. Then Saga was bought by Hydro, and then Hydro was bought by Statoil, and suddenly we have only 1 company. That was a very black day for all the people that do consulting. A lot of work here, a lot of paperwork. In fact, they say that the amount of paper produced in Norway per field was exactly the weight of the steel later on you put on because you have to do all that thing. But I think we've learned something about it, and there is also contractor that come and do a turnkey, and they start to find out how to do that less. But one of the bad things for us was that instead of 3 companies, we have now 1 company, and that's not so good. Okay, go ahead.
Thank you. So in this, for concept selection, the first step is to define the topside layout and weight of all the equipments, and also offloading a strategy to know, for example, what is the frequency of shuttle tanker, to specify the parcel size, and what is the frequency of offloading, and based on that, you can estimate if you need a storage, online storage. I mean, if your offloading system is not pipeline, it's just by shuttle tanker, you can estimate what is the required storage capacity. And based on that, you make initial sizing of the hull to support topside, riser, mooring weights, and also required storage. And you make a stability and motion analysis and calculate the loads. And then you make some simple structural analysis And based on that, you can make an execution plan for design, fabrication, integration, transportation, installation, and commissioning to estimate CapEx and schedule. And now you can understand why we have much more accurate cost estimation in this phase. Because in previous phase, you don't know exact weight of hull, so you cannot make any execution plan. And what you make is mainly based on previous experience or some rough estimation. And in this step also, you make a cost and a schedule estimation, and then you compare and rank the scenarios based on the available information. And also risk assessment is mandatory at the end. For the last step, to make a final decision, because even with the available information, cost estimation and time, maybe it is not possible to make a final decision, because maybe 3 concepts will pass your threshold and accept it. So then you make a risk assessment, and final concept is usually benchmarking or compared with the similar executed projects. But what is risk assessment? Risk assessment the type of risk assessment which we are doing is usually technical risk assessment, execution risk assessment, operational risk assessment, safety risk or safety assessment, and commercial risk assessment at the end. And what is tiebreakers that I mentioned previously, which is the final decision drivers. So when economic and performance indicators of 2 or 3 concepts is indistinguishable and it's difficult for you to make a decision, then operators usually use their tiebreakers, which means their strategies against HSE or towards HST, better to say, flexibility and mobility. For example, for HSE, when you have 2 concepts, that concept which give you more deck space or better deck space for layout. For example, when you have a let make one example for a disadvantage of 7 unit. So when you have 7 unit, it has a circular shape deck space. But when you have a ship shape unit, you have a square shape deck space. And this square shape deck space is much better for layout, because you can put all the train follow off each other, and also for safety issue is much better. And also you can put accommodation far from the high pressure areas like separators. But in circular shape unit or even for a square shape unit like SPAR or TLP, you have to put accommodation closer to the high pressure or, for example, compressors. So then if both concepts get to the final decision gate, definitely concept which give you better layout design or larger deck gives greater and better separation between the hazardous and non-hazardous area will be accepted. Or also flexibility. Scenario provides more flexibility both for contracting and to adapt to the reserve or uncertainty are preferred. For example, in one of our projects, when we end up to the final decision gate, there was 1 ship shape unit and 7 concept, but operator didn't accept that 7 concept because he feel that available shipyards doesn't have enough experience for constructing, and there is a risk of delay during construction, which was happened for Goliath. The COSCO shipyard in China delayed the project 1 year because this was their first circular shape experience.
What, in China or in Korea?
In China, COSCO, yes. And it was delayed
They've
by...
never done this thing before.
No, it was their first experience.
And it took 1 year longer than
Delay,
expected.
yes. And also project was also 1 year delayed because of the change in government in Italy. And now the project is 2 years behind the schedule. And also mobility. Also, for example, for marginal oil field, when you make because the average year of the superstructure or floating production unit is at least 10 years. But when you select a floating production unit for field which only have 5 years, you should have a plan to reuse it for another field. So then you should use a concept which can be relocated easily, like FPSO. But Yes.
Your vessel, is that considered a ship vessel? Do you have to have a captain and marine people, or is that
No,
structure?
It's a structure is same as semi-submersible.
The semi-submersible, you have captain. I mean, they have to move. They have to have. It's like they have to go to inspection in land. They
It's
have-
more closer to ship, yes. In this aspect, it's more closer to ship.
So one is on location, are going to be a captain there, drinking champagne and having a great time, and
Yeah,
having
they-
marine crew. going
Yes,
to
Monday
be-
afternoon they have a time with just some kind of celebration on board. Everybody are free to.
So it's what about taking it to land for inspection, or you do it on location?
Usually, one of the advantages for FPSOs is that you don't need so much onshore repair. We can do everything onshore, but sometimes you may need. But usually, when we design it, we design it for whole field life without onshore repair. But sometimes,
You have a ballast system, so you have people that are dealing with the marine part of it.
yes, of course.
The ballast,
System.
anchor system.
Yeah, because
they work.
Yeah, when we offload the unit will be completely empty, but then the draft of the unit will be quite low, which is not stable. Then we have to fill the ballast tanks to increase the draft to the safe level, which is
And if there
similar.
is a storm come, you have also to ballast it more or not. Or it's-
Usually for a storm, no, we don't, because we design it for the worst case. We use the minimum draft and maximum draft, and we apply, for example, 100-year storm or 10,000-year storm for both cases.
But you have storage on the vessel.
Yes, we have
You
a
fill the
storage
tanks, it's going to go down.
down, yes.
So you're going to
But the
work up and
differences
down.
is not because when the, for example, for penguins FPSO, when the unit is empty, the draft is 16 meter because the ballast tanks are filled. But when unit is completely full, the draft is 20.7 meters.
Okay, so
Because-
you have water tanks
And
you have oil tanks.
Oil tanks,
So when you fill the oil tanks, you empty the water tanks.
water tanks, yes.
Okay, but they are not the same tanks, they're separated tanks.
Yes, they are separated tanks, yes. And almost 40% of the capacity of volume of the unit is allocated to ballast, and 60% is allocated to storage of oil.
So all the time you fill one, you empty the other.
You empty other one, yes.
You empty the one.
Yes, it's like that. Okay, and now after you define your concepts, you have basis of design and functional requirement available in your head. Concept screening phase will identify all the basic building blocks, as you can see here, for example, which are subsurface team, enhanced recovery, subsurface subsea systems, enhanced recovery, drilling platform, production platform, export system, and onshore facilities. And these are different analogies you can have here. And then you combine this concept together to generate different facility development options or different facility development scenarios. Now,
What you call facility, or
the
what you
facility is all the structures from wellhead, if we have a subsea wellhead, up to the platform.
all okay.
I mean, mooring, risers, and flue lines, and
From the
Everything.
wellhead up.
from wellhead up to the
Umbilicals,
everything.
risers,
Risers, everything, yes.
anchors in your case also.
Yes, of course, anchors and or dynamic positioning systems. So now we will explain each of these basic building blocks. The first building block is subsea system. A subsea system building block consists of an assemblage of trees, wellhead, manifold, as you can see in this picture, jumpers, which connect manifold to the wellhead, pipeline end terminations, umbilicals and flue lines, and there are two basic building blocks. You can have a single wells tie back to the floating production unit, or if you have several wells, you can connect several wells together by a manifold and then tie back this manifold, as you can see, for example, here to the floating production unit. And subsea architecture design is mainly driven by number of wells, location of wells, distance to the host unit, subsea bathymetry, fluid properties to determine flue line dimensions, and arrival production rate, temperature, and pressure at pipeline end manifold, which connects the flue lines or risers to the floating production unit. And also, for some reservoirs, or better to say, for all reservoirs, you need some recovery method, because for this recovery, you may need some extra equipment on board. Therefore, you have to specify the required recovery or enhanced recovery methods. For example, basic building blocks are downhole boosting, gas lift, or gas injection, water injection. For example, when you need water injection, you have to allocate water pump and consider some space and also some payload for that. Or maybe if you have a very complicated reservoirs, you need a secondary and enhanced recovery method like steam flooding, fire flooding, chemical injection, and polymer injection. And also you have to specify, based on the drilling functionality, you should also specify drilling building blocks. Selection of the drilling package depends on the size of the reservoirs and type and distance of the wells. So basic building blocks are tender assisted drilling rig, mobile offshore drilling rig, and permanent drilling platform. So this is second choice, mobile offshore drilling unit, that you have a floating production unit here, and then you have a leased, or maybe if you have enough money, you have a dedicated mobile offshore drilling unit in a site, which give you the well service requirements. So for this case, when you have a satellite well system, you have several wells quite far away from each other. With subsea well system, you have a Christmas tree on the seabed. Then you should use mobile offshore drilling unit or drill ship for well services, because then your floating production unit is far from the well and you don't have access to the well. And for some services, you need direct vertical access. But if you have a single drill center, like this case, which is a TLP, and surface well system, then you can make or give all the services for the well from the floating production unit, and then you have two choices: tender assisted or full drilling package on the platform, which is called drilling platform as well. And these are three examples. For example, this is a mobile offshore drilling unit which can be used for work cover and well intervention system. When you have a wet tree and satellite well system and you need heavy work cover, which is and when you have a dry tree system with well cluster system and you need heavy work cover, and you have dry tree system on your floating production unit right here, but you have limitation for payload, because full drilling package is quite heavy, and for some platform like TLP here, TLP is very sensitive to the payload, because when you increase the payload, then you reduce the tension on the legs, and this can increase the horizontal motion. Then you can put the drilling package like mud pump and everything on separated units, and when you need the service, this unit can come and connect to the floating production unit and give the service to the drilling package on the floating production unit. This solution is called tender assisted drilling. But if you have a large floating production unit like a TLP Mars in Gulf of Mexico, and you have enough deck space and you have also enough payload capacity, then you can put full drilling package here together with production unit. And this is some simple guideline for early decision on type of key platform functionalities, which tell you if you have a small reservoirs with single drilling center, so it is cheaper solution to have a wet tree system. For example, you have only 3 production wells, because if you want to use dry tree system, then you have to use more expensive facility or floating production unit, because TLP and SPAR, which provides the dry tree system for you, are in general more expensive than ship shape unit or semi-submersible. So for if you have a small unit and a small reservoir, single drill center and wet tree system, then the best solution is only to have a floating production unit without drilling package. But if you have a large reservoirs, stacked or compact, but you can have a single drill center, so then dry tree system is the best solution, and it's better to have a full drilling package and floating production units.
And you have a big issue. You have to live with simultaneous drilling and production.
Production, yes.
And that's a not unpleasant situation.
Yes.
Not for the drilling and not for the production.
Production.
Every little instability in the wellbore, the driller closed the well, but you have to shut down the plant.
Production as well.
Oh, there is some downside.
And these are host platform building blocks. Host platform usually consists of these main subsystems: topside, hull, station keeping system, and riser system. First, we specify topside. Usually topside design and layout design. They just give some geometry from us. They know that, for example, in our case, is a circular, and then they try to make a layout as close as possible. And then they make a weight estimation and give it to the marine department. Marine department just estimate the required size and make the analysis for a station keeping system and riser system. So this will be.
It's a very interesting drawing, because number 10 and number 1 and number 2 shallow water, and they're all bottom supported.
Bottom supported. Yeah.
All the rest are not. Can you give a few words why the deep water go to this? And
yes.
Why not to make a bottom support very long?
The main decision factor is cost, actually, because for fixed platform, if you just make a graph which shows the cost versus water depth, this will not increase linearly. This will increase almost exponentially. Suddenly, after some water depth, like 400 meters away, it will increase significantly. For example, if you go from
Why?
Because
Why
because of the moment on the unit, when you increase this moment will be quite high, and then you need much more stronger structure. Maybe you can just model it by single beam. That when you increase this beam, then you have much more load on that in the water depth. That then you need much more stronger structure, and then substructure cost will be much more. And also installation would be difficult also for fixed structures. But here, when you go to some water depth, as I mentioned earlier, the maximum water depth that fixed structure solution or jacket type structure have been used up to now is 420 meters. But also we have a gravity-based platform which have been used into 600 meters, like Troll A. Yes.
Number 3 and number 6.
Yes.
Why one of them is connected into the seabed and the other one?
Oh, it's also connected. It's just it should be connected.
No, 3 and 6.
Okay, 3 and 6. Okay, 3 is also connected.
Yeah, 3 is connected.
Yes,
6
3
is not connected.
6 is actually connected by these mooring lines. This is connected by these mooring lines, which shown are up to here, and these are risers. So when you go to the deep water, so if you just compare these two concepts with each other, you can just realize that how can large be the cost of this part compared to this part. This part is just few number, for example, 12 number of chain with a diameter of 167 millimeter. But here you need several pipes with a diameter of 2.3 meter, 2.5 meters. So then you can understand why it can be more expensive. So and then host platform, you have different options. You can use use host platform with drilling and workover package on board, or with only workover package and drilling can be done by a separated mobile offshore drilling unit, or without drilling and workover, just topside with production facility on. Yes, please.
In deep water or ultra deep water, the vertical movement, the vertical weight, the height of the waves are the same than in shallow water, less, shallow water.
Actually, in deep water, because you have more severe waves, you should get larger vertical motions. But when you are in deep water, system is flexible in vertical direction because of type of the mooring system and riser type you select. We give first, for example, in our design, first we calculate the maximum heave motion, and this maximum heave motion will be used to design riser system. Then riser system should be flexible for that. And for some solutions like this, TLP doesn't have any vertical motion. It's just behaves like a fixed platform. And these are the typical type of floating production unit: FPSO, SPAR, TLP, and semi-submersible.
Which number is the SPAR?
So yes, these first two type are different version of TLP, tension leg platform.
4 and 5.
4 and 5. And number 6, as you can see, their mooring system, or the wires that connect the unit to the seabed, are under tension and vertical. This is why they call TLP, tension leg platform.
So the tension eliminates the need to have anchors.
Yeah.
Because the vertical pushing, if you move aside,
Yes.
it creates a lateral force
And
bring
bring
you
it
back
back.
to
Yes.
position. So you're just in tension, you don't need any anchor. That keeps you the tension
Yeah.
down, keep you
Yes.
limited the side motion.
Side motions, exactly.
Okay.
Yes.
But the others that don't have tension, you have to put anchors.
Yes, you have.
Oh,
Actually, here the anchors are just some vertical anchors under tension.
Okay, but it's basically kind of a tension member.
Tension members.
The only problem that we have with that, where the well ends up. Because somewhere the high pressure part of the well is until the wellhead. Whether it's on the bed, seabed, or on top. If you put the dry tree on top, then the question is, will you bring all the way the full pressure of the well all the
Up
way
to
to the
the
platform?
platform.
Or you stop it down there, you make kind of a wellhead at the bottom, and then you, with a valve even, and then you make a connection which is riser, which is a low pressure riser. That's a big issue in where the well is ended. Because the TLP, there is a tree on the top.
On the top.
But there is another tree on the bottom or
Bottom
not?
also.
What is the status of this? Is that part of the well or is that the riser?
I think this is, as far as I know, it's optional. Depends on the.
But it's a different
Yes,
requirement.
it
And everything which is part of the well is much more because there's no protection.
Yes,
Okay?
this depends on the motion of your TLP. So because you have a pressure in the risers, and then if with the high pressure in the riser and motion of the TLP, you are still in the below the safety margins. You are allowed to leave the pressure of the reservoirs to the top tension risers. But if your motion exceeding the safety limits, then you are not allowed to just put the total pressure of the reservoir to the risers.
Because we're allowed to have a hole in the riser.
Yes.
We are not allowed to have a hole in the well.
Well, yeah.
So if legally the well go all the way to the platform, you get a hole in the riser and the one go to the sky.
But at least for the project which I have been working up to now, we always had the one valve. Even we have a dry tree on the system. We had the one valve at the wellhead.
Okay, so basically
There.
the well ended in the seabed.
Okay.
You
Yes.
can always close it there.
Close it
something
there.
like
Yes.
that. The riser, it's okay, but you get the hole, you get the break.
But previously it was not like that. After some blowout, and also after this deep water horizon, there is always a requirement for one valve at the seabed or inside the.
So basically,
Yeah.
this riser, it's riser. It's not extension of the well all the way to the dry tree on top. I
It
think
can
they
be,
would have in
yes,
in
it can be.
have it here.
But because also recently one of the new solutions is high pressure, high temperature risers that can take over whole pressure of the well inside, which are known as high pressure, high temperature.
Can you go further and explain the various on the drawing and how do you call each one of them? So you show us the
Yes.
tension leg, TLP, that
So
was 4 and 5.
4 and 5 are two different solutions of TLPs,
Okay?
and number 6 is a spar, which is just a vertical column, and mooring system is just like a catenary line that allows the unit to move laterally up to, but this lateral, for example, when we analyze this spar unit, we calculate the lateral motion, for example, for it should be around 20% of the water depth, the maximum lateral motion. But if you have a two lateral motion, like 20% of the water depth, then you have a limitation for the type of riser. But here, for example, this concept which is shown here probably had very limited lateral motion because you have a dry tree system on that, because you have a top tension risers or vertical risers. But next solution is semi-submersible. Next two solutions.
Excuse me,
Yes.
do they have storage capacities, spar platforms?
A spar has little storage capacity because it's not so sensitive to the payload, and the reason is that why you need a storage capacity here, because for example when you have a pipeline system, you may have a failure in the pipeline system. For example, the pipeline system which you are connecting to that is quite old pipeline system, and there is a high risk of failure in this pipeline, and then you should estimate, like for example, 1 week of shutdown or 1 week of stopping export. Then you should consider sufficient storage here for example, few days, just not more. But a spar can give you some storage space, but not TLP, and also FP semi-submersible also. But they don't use as a storage unit. If you want to have a storage available, which I'll explain later, you should have one, for example, shuttle tanker close by to use as a storage. So these are number 7 and 8 are semi-submersible, and number 9 is floating production, storage, and offloading. Yes.
Number 6, you have these spirals on the cylinder.
Yes, this spirals actually, because you have a long cylinder, and in area like Gulf of Mexico, which you have this loop current effect, and you have very high current, like 3-4 meters per second, which is quite high. This can make some vortices around the hull, and these vortices will make some vortex-induced motions. And to reduce that, this is just a standard solution for circular body in high-speed flow. These spirals around reduce these shedding vortices, and then reduces this lateral motion. And even on the risers, if you have a high current like in Gulf of Mexico, they still use these spirals on the riser and the pipe to reduce just lateral motion. So maybe we should go ahead. So selection of the host platform depends on the functional requirements, and different host platforms are different in these functionalities. For example, some platform can support drilling and workover package, but when you have a small FPSOs, because you don't have enough available deck space, you cannot put any drilling and workover on that. Or some platforms can support dry tree systems, but all platforms can support wet tree system. Or some platform, as you mentioned, though, they don't have any storage capacity. So if you are working in an area that there is no pipeline available, so you cannot use this, for example, TLP system, because TLP needs pipeline, available pipeline, and if you are far from market, then it will be too expensive. And main differences in the motion is for heave and pitch motion, which is this motion and this motion. And these two motions are mainly important for riser design because they are the main motions that induce fatigue damage to the risers. And also there are differences for execution risks like construction, installation, operation, abandonment, and reuse. And these are the major differences between the different platforms. And this is also again a simple table that can be used as the initial decision tools to select platform. So here we have different varieties of these platforms, their main functionalities, if there is any constraint, if there is any constraint for offshore installation and decommissioning. And also one of the building block is export system, that you have two solutions, exporting by pipeline, exporting by shuttle tanker, which depends on the distance to the market, distance to the available infrastructure or pipeline. And if you have a possible method is oil and gas pipeline, direct shuttle tanker offloading, that for example you have a floating storage unit without any storage, then you should calculate the frequency of offloading, and then you should allocate, for example, 2 shuttle tankers close by, and when one is full and going, another one is connected and another one is coming to the queue. So there is always one shuttle tanker online. But if your system has a storage capacity here, you can have shuttle tanker offloading plus floating storage unit. For example, if you have a spar without a storage, you can have one floating storage unit behind, which is just a overage shuttle tanker, and then another shuttle tanker is coming and offloading from this floating storage unit. And if you have,
How it works in Arctic, I mean transportation, because of cold temperature, it causes some problem with transporting gas or something.
but you have a shuttle tankers designed for Arctic region. They have icebreakers in front. You should use them. Yes.
Are these floating units permanent or not?
Floating production units?
Yeah. are
Yes,
they-
there should be permanent. They are more at locations. But when shuttle tanker is coming here, if shuttle tanker has a dynamic positioning system, it's just few propellers on the bottom of the tanker and keep the tanker in position, and then you connect the flue lines and you start offloading.
But what about the capacity? How is it calculated? Like if it's the first producing well, you cannot really know without before drilling and producing.
Okay, so you should make a just estimation of the flow rate, and then you design based on the plateau, the maximum production rate, and then based on that, you should calculate or check the availability of the shuttle tanker fleets, and to see which shuttle tankers are available for you and at which frequency. And even you have to have available meta-ocean data to calculate the uptime period for offloading. And then you can estimate that, okay, so this will be my parcel size, 300,000 barrel, and my production is such as this, and I have to have, for example, 50% margin. So then storage capacity should be 450,000 barrel of oil. And my parcel size is 300,000, and based on the production rate, shuttle tanker should be available on site every 4 days. And then you should plan for the shuttle tanker and be sure that you have always shuttle tanker available. Otherwise, you have to shut down the production, which can cost significantly.
Is it part of the same design or separate design?
At this size of shuttle tanker is a part of the design. Parcel size should be one of the input parameters for design, which has been calculated earlier by operator based on the available shuttle tanker fleet. Okay, so and then beside your offshore facility, maybe it is economical to have some onshore facilities like tank farm or LNG plant or even gas to liquid plant or gas to wire plant. So now we are going to the example. So this is the example. Our case study is a gas field. So let's assume that we are at the end of exploration and appraisal field, and this workshop for concept screening has been held, and they have made this concept screening matrix. So which includes different hub. We have a gas field, different well types, different transportation methods, and different number of wells. If you multiply all of them together, you will end up with 128 different solutions. But it's difficult to calculate the cost for all of these solutions. So first, you need to make some technical feasibility. After first stage of technical feasibility, for example, so you know that if you have a FLNG system, then there is no meaning to use pipeline system, because if you have a FLNG system, then you can have FLNG carrier. Then pipeline is there is no meaning for pipeline. So if
but you have FLNG, before you liquefy the gas, you have to extract the liquid, so you have condensate, so you have to find a solution.
Also a pipeline for condensate, that's
But
correct.
let me ask you a question. If you want to do similar exercise to the students, you have kind of nice, like, how do you draw all these things? Do they have a special drawing program that you have rig and chips, and how if you go to the next figure,
Yeah.
you have, if our students want to do this drawing, what they cut?
Now
and
this
do,
is just symbolic drawing. It's not
it's symbolic, but do you
this
have a program that makes this symbolic thing, or
usually.
database of these symbols?
Yes, usually there is a program which we are using for 3D visualization called PDMS or CATIA.
Anyone heard about it?
And after you make a 3D program, you can ask the program to make just a 3D view of a structure like this for you.
But do they have kind of ready objects that you just call and lean and power?
In some
it's a
software,
manual thing,
yes,
yeah.
I saw, for example, in Oil and Gas Manager, we have a symbolic FPSO, symbolic TLP that you can directly use it.
This program of Siemens.
Yes, this Oil and Gas Manager.
Oil and gas.
But usually people, they just, in the big company, they have just a library of these objects provided during their projects. Or when somebody is writing some book or something like that, they just search in the internet and find one's
Okay.
typical pictures.
Now you got the solution. Search on the internet,
Yeah,
take an
this-
image and put it. If you'll get an exercise to design a field.
Yeah. So here, so as you can see, after first technical feasibility analysis, we have ended up with 12 different solutions or scenarios. 4 subsea wells, 4 wells, 6 wells, 8 wells, and 10 wells, and 3 host platform. But here I just also consider subsea tieback as one of the solutions or one of the host platform, but this is not a host platform, it's just one of the solutions. So subsea tieback, semi-submersible, and jacket. So and then based on my available databases or using commercial databases, I will calculate net present investment, which includes capex, drillex, opex, and abandonment costs, total cost for each concept and for each number of wells. So cost of infrastructure, drilling, operation, and abandonment will be this amount. And then I will calculate net present value based on hydrocarbon sale price and production profile, which you are quite familiar with that. So now I have net present value and net present investment for each concept. And then I make a plot like this. X is net present value and y-axis is utility index. Net present value over net present investment. And then,
what is net present value? We know net present investment. What is that?
yes, net,
Does this part of the net present, because the investment go into the net present value?
yes, of course.
You have minus, you have plus.
Exactly.
So you take this part which is minus,
Net
that would cost you?
cash inflow minus cash outflow, including discount rate.
Okay.
This is just a,
So this net present in value, that's the cash out,
yes,
everything. That
Yeah.
would cost you.
yes,
Okay. And then
the total
this
income.
one, divide net present value of that divided by the total net present value.
Divided by net
Tot-
present investment, that actually the cost of the project, including capital cost, drilling cost, operation cost, and abandonment cost.
Don't understand. Net present value include the cost and the revenue.
Yes, yes.
And now you say, let's take the cost divided by the total, cost plus revenue. Is that what you do?
No, in net present value divided by net present investment.
But in net present value, we have already investment involved.
Yes, sure. Yes,
So
of
yeah,
course.
so what you say is the costs, part of the cost divided by the total, the net present value. That
Is your income what
the
you
capex.
left after all the costs for you? What left for you?
So it's the capex divided by the total net present value. Which
No.
is capex and opex and drillex and you name
It
it.
is a profit divided
Opposite.
by the investment.
Yes, the profit. Yes,
Profit
it's
divided
a
by the investment.
profit divided by investment.
No, it's not profit because okay, profit you already in this calculation of the profit you have all the cost.
Yes,
At
of
the
course.
beginning it's
Yes,
minus and then it's
Yes. Yes, it's actually A minus B over B.
Okay.
Yes, this ratio.
And typically how much this number kind of 3, 2, 5?
Actually, I don't have any idea about that.
Okay.
They don't keep.
Sorry, the numbers that were on the table before, those are in what,
Millions.
dollars, millions?
Yeah, so it's
Yes,
billion,
of course.
billion,
Yes, of course.
1.2 billion,
$1 million.
2.6 billion. So this dollar.
But I have some tables output from oil and gas managers. If you want, I can just provide you these tables.
Well, I
but
think Nila,
Huh?
when he make the exercise,
yes,
he's going to ask you.
yes, definitely, no
Because
problem.
otherwise, every one of the students going to call you separately. You don't want that.
Yeah, no problem.
So we'll get for you some table that you suggest hypothetical numbers
All right, yes,
if you
sure.
want to make an exercise.
Sure. So then you have this graph here, which shows utility index, net present value or net present investment against net present value. And then the decision strategy is to select concept that maximize net present investment and utility index simultaneously. For fixed platform and semi-submersible, you can see 6 well case is the case that you have net present value and net present and utility index maximized simultaneously. But for tieback, 4 well maximize utility index and 6 well maximize net present value. So it's difficult to make a decision here because it's not straightforward. But you know that based on the strategy of the operator, or there is a risk of losing one of the wells during production. So then operators knows that if they use 6 wells case, losing of one well will be only 17%, for example, of the production. But in 4 case well, losing of one well will be 25%. So it is better to use 6 wells case here. But here, because if you have a rough estimation and you need to make a stochastic analysis and calculate and evaluate that which solution is more reliable. So the formulation is like that. Because why your cost is not accurate? Because you don't know the exact value and you have some range of value. For each cost prices, you have one minimum number, one maximum number, and one medium value. For example, assume that you have take the numbers from 10 different resources, and these 10 different resources give you, you can calculate mean value, medium value, minimum value, mean value, and maximum value. And then you assign a triangular shape distribution to each of these costs.
So this median is basically the mode.
The mode, yes, the mode.
This is the mode. Okay.
Mode value.
And you assume it's in the middle because you don't know anything.
Yes, just you have
You
to.
assume that the mode and the mean
Yeah.
and the medium are all the same.
Yes.
Okay, that's assumption.
So, and then you have probability density function for each cost parameters, and then you calculate. So this is triangular shape distribution, and you can calculate cumulative distribution function for this distribution, and then you make a what we call it white noise. You just generate a sample of numbers between 0 to 1. because cumulative distribution function is a value between 0 to 1, and based on these numbers, population of numbers 0 to 1, you calculate the associated value of these cost parameters, and then you have a population or sample of cost, and then for each sample you calculate net present value and utility index. For example, here we only calculated net present value for each population, and then we calculate cumulative distribution function. Is just a straightforward calculation, and then you plot all of these against each other. For example, here it has done for different number of wells, and based on that, if you just draw one vertical line here, you can easily identify that case with here 10 number of wells is most reliable case for you, or cost estimation for 10 number of wells is more reliable for you. Or here 6 number of wells is less reliable than 4 number of wells, which can help you about the decision in previous step, that whether to select 6 well or 4 wells. So, but here we only included the economic parameters or cost parameters. If you include non-economic parameters like a schedule to first oil, this final decision may be different. In the previous slide here, as you can see, semi-submersible is here because we have assumed that we need 3 years from sanction of the floating production unit construction up to first production. We need 3 years for all of them. But actually, semi-submersible takes in average 5 years. So if you include these 5 years in net present value calculation, then semi-submersible will move back to the left. Net present value will be much less than previous calculation. And this tells you that this is just to show you that economic evaluation alone is not sufficient for final decision, and you need to include all your parameters and all the parameters in decision. And for both for concept selection and concept screening, you need to compare or rank the scenarios based on qualitative parameters. And for qualitative parameters, for ranking based on qualitative parameters, there is a standard approach which is known as analytical hierarchy process, AHP, a decision-making method to prioritize concepts under qualitative multi-attribute decision drivers. When you have 3 concepts and you have to compare these 3 concepts against 8, 9, 10 different quantity or properties, better to say. So in this step, first we have to select the attributes that can make difference between these concepts. Otherwise, you have to evaluate similarly all the concepts together. And
if you, when you got married, if you would go through all this analysis to decide if you want your wife or another one, you'll never get married.
yeah.
And that's, you know, something
Yeah.
personal. That, and we don't do that. We just use intuition.
Yeah.
So I think we still use intuition here as well.
Yeah, but in offshore, in shallow water and onshore, as you said, field planning were mainly based on previous experience or even personal experience. But because in deep water offshore, it's more high risky and it's more costly now, and also when you are going towards marginal oil field, then concept selection in this structure way became much more important.
We are reaching the time that we have to stop, otherwise they'll start to storm us.
Okay,
so
yeah.
if you're just more
Good.
selective and
Yes, okay.
and we'll try
Yes,
to
we are
sum
almost
up.
at the end, yes.
I think we got most of the answers right now.
Yeah. So here you should select attributes and sub-attributes as we mentioned before. So here as an example, examples of attributes and sub-attributes. For example, operability is one attribute, but if you want to be more detailed about operability, you can divide it into some sub-attributes. Is to start up or shut down. And fabrication or installation is to fabricate or is to install. For example, FPSO is much more easier for installation aspect of view than TLP. And then you need a ranking system to rank these attributes. One of the standard ranking system is like that you have these different grades, and when you compare two attributes with each other, attribute A against attribute B, or better to say concept A against concept B. So then if attribute A is absolutely more important than attribute B, then attribute A receives weight of 9, attribute B will receive weight 1/9. So finally, first you should make a weighting system for attributes. You make a matrix like this that you have in first column attributes and in first row against attributes, and then you make a pairwise comparison. Operability versus operability, okay, weight 1 because they are equal. But whether operability is more important for you or fabrication and installation. So this is something based on personal idea, and a team of people will make a decision about that. So you have some people from construction part involved in the team, and then each of them give one of these weights, and then you make an average, and then the average will be close to 5. You assign 5 here. But when you are comparing here fabrication against operability, it will be 1/5. It will be 0.2. And after you made all of these pairwise comparison, you normalize all of these columns. You just sum out all these 4 numbers, 2.5, and then you normalize these numbers. Each column will be 1, and then you make a sum for each rows, and then you make for one single number, which is how important each attribute against other attributes. Also, you will do this for sub attributes, and you get same weighting system here for sub attributes. And now you compare each concept against each attributes with this weighting system: excellent, good, average, or bad. Or just ask the surface facility team, how good is fixed platform with respect to ease to a startup or shutdown? Is it good? Is it average? Is it poor? Okay, so most of the people said it is good. So you put 3 here. And you did do this for all the concepts, and then you multiply these weight here to the weight of attribute to the weight of sub-attributes, and you put them here, and you make a sum here. And finally, you end up with 3 different numbers, which is quite easy to make a decision. So this is how you compare them together. But when you compare the results, for example, during the concept selection phase, it was just based on the economical indices. It tells you tieback, semi-submersible, and jackup is best, better, and good. But when you include non-economic system, you will end up with different decision here and here. So it's difficult to make a final decision. Therefore, you can get help from risk assessment. And also, maybe I also should mention that because this multi-attribute decision-making model is based on personal opinions and personal experience, and it can be different from one team to other team, or even from one time to other time. So therefore, you should do the same what you have done Monte Carlo simulations in the previous step for net present value here. You just define some minimum, medium value, and maximum value for each attribute's weight, and then you do Monte Carlo simulations to find the distributions for these final weight numbers you found. I mean these numbers here. You just get a distribution for these numbers, and then you take the mean value or most probable maximum value, most probable value for each concept, which you will get it here. For example, for this case, after Monte Carlo simulation, we end up with the same order of numbers here, which confirms our deterministic calculation before. But then when we go to risk assessment has also same procedure as multi-attribute decision-making model. First, you should make a list of all possible risk events from previous records if you have, or from failure mode and effect analysis for different system and subsystems. And then you should assign probability of each failure. which can be based on previous record, or most of the time is something relatively. For example, is very high, is medium, or is low. You cannot assign some accurate number like 6.5 to that. So, and also you should specify attributes can be affected by this failure or risk, which are mainly health, environment, asset value, and project schedule. And then you should assign probability for each of risk or failure modes, which we have here. We have a weighting system of 0 to 5. The 5 means it's quite often happen, and 0 means it's never happen. And also in risk ranking, we rank the people who are or devices which are risk takers to aggressive or conservative. Because, for example, when you ask a designer what is the failure rate of mooring system, designer said, for example, is medium. But when you ask operator what is the failure rate of the mooring system, operator says high, because designer always believes that his system never fails. But operators, because he's working on the platform, the number he told you, or if both say medium of the operator means more severe than medium of designer. And you have to weight these opinions here, whether it is aggressive person or conservative person. And after that also we have a weighting system to specify how severe is the risk of or impact of risk event on the attributes, which we have this standard weighting system recommended by the societies. So if, for example, the failure can make a fatality or a serious impact on the health and safety, it should be exponential or 5. Then at the end you will end up with this risk matrix calculation, which here you have a risk events, all the risk events identified by the expertise in the area, and then probability of each failure. And also after factoring this probability of failure, and here you have attributes, and then you do some calculations together, and you will end up with some numbers here for each risk failure, which finally the sum of all of these numbers will be total risk of concept. So for risk assessment you will end up with one single number. And now this risk weight will help you to identify this concept from each other. So here you will finally make these two tables, one with multi-attribute decision making model and risk weight, and one will risk weight and net present value. So here it is you should select the concept that minimize the risk and maximize multi-attribute decision making model. So it's difficult to decide because this minimize the risk, this maximize the multi-attribute decision making model. And when you come here, this concept minimize the risk and also maximize net present value. Here it's easy to make a decision, but here is not. But how you should make the final decision, it's tiebreakers and operator strategy. So now we end up with conclusion. As we mentioned, concept selection for deep water field development is a multidisciplinary task and needs contribution from all the key stakeholders: subsurface team, drilling and completion, surface facility, operation and maintenance, management and commercial team. And you need a structured methodology to generate, screen and select the right development concept. And concept selection is performed when uncertainty in the critical parameters which determine commercial success of the project is high, and addressing subsurface data uncertainty in the facility design phase is important. And deep water facility design is highly dependent on subsurface data. And success of field development planning highly depends on quality of the information, skill of subsurface team, technology and reservoir modeling. And these are a list of references that I'm sure you can find. All of the information are present for you in this presentation. You can find in these 8 references, and these are all of these 8 references is available. I can give a copy to the professor, and which can share it with you. And also all of these references are available online. Don't worry. And at the end, I would like to appreciate Professor Michael Gul.
Well, I think we have to
Gulen and Miran Spector for giving this opportunity to be here.
Actually 3 hours, and we took 10 minutes at the beginning fixing the studio, so he basically stick to the time. Of course, the latest part at the end is the more analytical. The first part is kind of visionary. We put them both together, but in 3 hours. So we really appreciate and thank you very much. But it's only the beginning.
Yeah.
Because I guess Milan's sitting now and his mind is working. Of course, we have to have data and we have a few type of analysis, but you have an opportunity to experiment a little bit with this concept. I think you get a good picture what is available, even if you absorb and retain 20% of that. I think it's very good. We don't expect that you retain 100% what says here. And then we identify 1 or 2 things and let you work with it 1 week, and I think then it will become clear. So thank you very much.
Yes, welcome.
Let me just stop
Very
No, it's here, it's here.